Hello and welcome friends. In this particular module, I wish to discuss some contents related with tachometric surveying. Here, we will discuss the definition, various applications, features of the tachometer, various systems of the tachometry, distance elevation formulae, determination of the tachometric constants, and we will also get introduced with the concept of tangential tacheometry and use of subtense bar. Here, as you go through the content, you will be able to demonstrate use of tachometry as a surveying technique. We will also be able to work out the constants of the tachometer and also to introduce use of tangential tacheometry and subtense bar. Basically, this particular word tachometry has got Greek origin. Literally, it means fast measurements. The word from the Greek is Tacheometer. This is convenient system for rapid surveying. The system is also known as Tachemetry, Tachemetry, or Telemetry. It is a branch of angular surveying in which the horizontal and vertical distances of various stations are obtained indirectly by making use of optical means. Hence, this method is under the category of optical distance measurement, abbreviated as ODM, as it involves the determination of the horizontal and vertical distances by making use of optical means. The ordinary process of measurements by tape as well as chain is thus totally eliminated. The primary object of this particular method is preparation of contoured maps or plans requiring both horizontal as well as vertical control. Also, whenever we are dealing with the surveys of the higher accuracy, it can be employed as part of check surveys. The method is rapid as well as convenient, and it is best adopted in obstacles such as steep and broken ground, deep ravines, waterlogged or swamp, and so on, which otherwise makes the use of tape and chain for distance measurement difficult or impossible. There are a number of applications being surveying technique. However, tachometry is mostly used in rough terrain where direct measurements are not possible. It is helpful for the preparation of the topographic maps which require both elevations as well as the horizontal distances. It can be adopted in survey work when the terrain is difficult and it is not feasible to employ certain direct surveying methods. Whenever we deal with certain major surveys, in order to fill in the details of some traverses, the method is very useful. At the reconnaissance phases of the surveying, it can be very beneficial. As discussed previously, this particular method is useful for applying the checks in major surveys. As well, whenever we are dealing with certain water bodies, it is not possible to make use of tape, chain and such direct distance measuring equipment, and hence in hydrographic survey also this method can be useful. In order to facilitate the measurement, the basic equipment employed is nothing but the tachometer. This tachometer is ordinary transit theodolite fitted with stadia diaphragm. So basically, as we make use of various theodolite, and we see that all the theodolite in the market that is available today are provided with stadia diaphragm. As such, all the theodolite that are available are nothing but the tachometer as far as this particular definition goes. Here, the stadia diaphragm can be in number of forms the way it is depicted here. As you see, here the horizontal hair as well as the vertical hair are the basic references. In addition, there is upper stadia, there is lower stadia, which are provided in the same plane of this horizontal as well as vertical hair. Some other features of the tachometer. This telescope could be simple external focusing, which is equipped with an analytic lens, or it could be internal focusing telescope. It is also having some additional features such as the multiplying constant has a value of 100. We will discuss more about this particular multiplying constant as we proceed further. The axial horizontal hair should be exactly midway between the upper stadia as well as lower stadia. The telescope is truly analytic. Again, this term we are going to touch as we move ahead. Additionally, telescope should be powerful, having the magnification of 20 to 30 times diameter to make the graduations very clearly visible for longer sights. The objective should be 35 to 45 millimeters in diameter to have sufficiently bright image. Say for small distances up to 100 meters, we can make use of our ordinary leveling staff that is commonly employed for leveling operations. If the distances involved are greater, then one can employ the stadia rods. So this particular stadia rod is usually a one piece and has 3 to 5 meter length. The stadia rod could be graduated with 5 millimeter divisions for smaller distances, while when we are dealing with certain longer distances, the rod could be graduated with 1 centimeter. As a technique, we can categorize this particular tachometry under different heads. First being the stadia system. It could be divided into two classes. One is fixed hair method and second one is movable hair method or subtest method. Another method is tangential system, and the third category is tacheometric measurement by means of special instrument. So under this category we can deal with some specialized equipment, which could be like say Beeman's stadia arc. In fact, this particular method is more of a academic interest today, and Beeman's stadia arc or such additional instrumentation is almost obsolete. Hence, we can think of some directly reducing tachometers as special instrument for present conditions, which I haven't discussed in this particular presentation, but in some other presentation we can discuss that. So, in this particular study assisting or tangential assisting, the principle is common and it is based on calculating the horizontal distance and elevations by observing the angle of the line of sight subtended with respect to known ordinate on the staff and the angle subtended by line of sight to that particular staff station. So, we will discuss more about the fixed hair method now. As name suggests, in this particular method, the tachometer employed provides the stadia hairs at certain fixed interval. So, the way you see here in this particular sketch, with respect to that particular horizontal hair, the upper stadia and lower stadia is kept at fixed interval, whereas this axial hair is provided exactly midway between that upper stadia and lower stadia. So, this staff interval or the intercept on the leveling staff depends upon the distance between the instrument station and the staff. The reading corresponding to all three hairs are taken on vertically held staff in this particular method. The staff intercept, that is the distance in between the two staff readings corresponding to upper stadia and lower stadia, is regarded as S, which is nothing but this staff intercept. Here, as you see, this is the axial hair. So this axial hair reading or the line of sight corresponding to that particular axial hair helps us to measure this particular vertical angle theta. So for such inclined line sights, the reading could be taken by keeping the staff either vertical or normal to the line of sight under this particular category of tachometry, but we'll touch this particular part, that is keeping the staff normal to the line of sight as we move ahead. But please keep in your mind that mostly we'll be discussing about the fixed hair method, as well as under this particular method the staff is kept in vertical manner only, because this particular method is most common method, and usually whenever we say tachometry we refer to this fixed stadia hair method only. For the sake of understanding, as we consider one of the category, the other method, which is movable hair method, is also called as Subtest method. This method is very similar to this particular fixed hair method. However, here the stadia interval is not constant, but it could be variable. The way you see here, such kind of arrangement is made available to vary the distance between the upper stadia as well as lower stadia in order to have the observations corresponding to the position of the targets provided on the staff. Thus, in this case, the staff intercept, that is the distance between the two targets, is kept constant, while the stadia interval, that is the distance between that two stadia, are variable. Here, whatever the things that we do in case of fixed hair method, all that things can also be done by making use of subtest method. Third category is tangential method. So in this method, usually we deal with longer sight. Here, we do not refer to stadia here, but we take the readings corresponding to simply axial hair. So, in order to measure the staff intercept S, we take reading corresponding to two targets that are provided on the staff held vertically. As such, we have to measure two vertical angles the way shown here, theta 1 and theta 2, in order to determine this horizontal distance, vertical distance, as well as reduced level of a station under consideration. So, as I mentioned earlier, we'll be discussing more about the fixed hair method. This particular method is based on very simple principle, that is, the ratio of the perpendicular to the base is constant for similar isosceles triangles. So here this O is the optical center producing the rays OA and OB, which are equally inclined to the central ray OC. So this A2, B2, A1, B1 as well as AB are the staff intercept placed at the various stations with respect to station O. As such, the ratio OC2 to A2B2 equals OC1 to A1B1 equals OC2 AB. It is expressed as constant, and having considered the angle between ray OA and OB as beta, it can be expressed as 1/2 of cot of beta by 2. As such, this constant K entirely depends on the magnitude beta. Let's try to deduce the distance and elevation formulae for horizontal line of sight. As you see, we are expected to have the horizontal line of sight, say OC. So in this particular figure, O is the optical center of the objective of an external focusing telescope. This A, C, B are the points cut by three line of sight corresponding to three hairs, say upper stadia, lower stadia and axial hair. As such, these B, C, A are the positions of the hairs on the diagram. As you see, distance between the small a and small p is nothing but stadia interval, whereas at the staff, the difference in between the reading corresponding to upper stadia and lower stadia is nothing but staff intercept S. Here, with respect to this particular position of the staff and this particular objective, the focal length can be considered as conjugate lengths f1 and f2. Here, f is focal length of objective. The small d is the nothing but the distance in between the vertical axis of the equipment and the optical center of the object glass, whereas capital D measures the distance of the staff with respect to that particular instrument station. So, as we consider this particular figure, we can have this particular expression as F1 to F2 should be equal to S by I, giving consideration to the similar triangles. Again, as I mentioned earlier, this particular F1 and F2 are conjugate focal distances. We can make use of the length formula as 1 by F is equal to 1 by F1 plus 1 by F2. As we multiply both the sides by F1, we get the expression F1 is equal to F1 by F2 times F plus F. As we have this particular expression F1 by F2 is equal to S by I, so here we can substitute the same in this particular expression, and F1 can be expressed as S by F plus small f. As this horizontal distance is equal to F1 plus D, we have to add that D. So accordingly, here the expression that we get is capital D is equal to F by I times S plus F plus D. Here, this F by I is expressed as multiplying constant, that is K, the way we discussed about it in our earlier slides. Its value is adjusted to be 100, whereas this F plus D is expressed as additive constant, and it is nothing but C. By inducing some lanes in between these particular object glass and the eyepiece, which is called as analectic lens, usually this value of the additive constant is made 0, which is constructional feature of that particular tachometer. If at all, if the equipment is not provided with, say, an electric lens, the value of the C can be considered in order to determine these particular distances. So, this basic expression D is equal to Ks plus C is known as distance equation. So, in order to get the horizontal distance, the staff intercept S needs to be measured corresponding to staff readings that are related with the difference in between these particular readings corresponding to top and bottom steady hairs. So, for a given equipment, as just we discussed, this K is nothing but the multiplying constant expressed as F by I, whereas this F plus D is additive constant. For a given equipment, the value of this particular K as well as this particular C can be easily determined by performing these two methods. So, first method is, here the additive constant C, that is F plus D, is measured from the instrument, while the multiplying constant K is computed based on the field observations. So, in order to determine this, let's focus the equipment to some known distance, say some distant object, and let's have the measurement along the telescope to have the value of the distance between the objective and crosshairs. This value is nothing but the focal length of the objective. Whereas the distance in between the object glass and the vertical axis, if you remember the gauge that we discussed in earlier slide, is nothing but this G. As such, the focal length of the objective and the vertical distance in between the object class and the vertical axis as d can be determined. Hence, the value of additive constant f plus d can be easily determined. Now, as we measure the distance capital D, as we have set the star at such a known distance, we can make use of this particular expression d is equal to ks plus c. Here, distance d is known, value of additive constant f plus d is determined based on the actual measurements taken on the instrument. The star intercept s can be determined by determining the difference in between the upper stadia and lower stadia star readings. As such, the only parameter k is not known, which can be computed by making use of this first method. In the second method, we can have some distance, say 200 meters on fairly horizontal ground, and we can have the distance divided with some interval of say 50 meter. At each of these particular 50 meter interval, we can keep the staff and take the reading corresponding to that particular upper stadia as well as lower stadia. As such, here we'll be having the first expression with us, d1 is equal to ks1 plus c. So, with 100 meters distance, say, we can have the another expression d2 is equal to ks2 plus c. As you see here, we have the value of d1, we have the value of s1, we have the value of d2, we have the value of s2. Hence, we can determine the value of this particular k as d2 minus d1 by s2 minus s1. As we substitute this particular value with any of this particular expression, we will be able to work out the value of c. As such, for the 50 meter distances, we can get 4 expressions. Accordingly, we can make use of any of the equations, and we can have the series of values as say k1, c1, k2, c2, etc. So as we average out these particular values, we'll be able to work out the acceptable value of k and c, even if the value is not known for the given equipment. The way I mentioned earlier, for the tachometer, the value of multiplying constant k is said to be 100, whereas the value of additive constant usually is made 0 by inducing the analytic lens. The way we mentioned about the horizontal sides, in the similar way, we can deduce the expression for distances for inclined side, which is major feature in tachometry. Here, P is instrument station, Q is star station, M is position of the instrument axis, O is optical center of the objective, A, C, B are the point corresponding to readings of the 3 hairs, S is star intercept, I is stadia interval, theta is the inclination corresponding to that axial hair with respect to the horizontal plane. Capital L is nothing but the distance measured along the line of sight. Capital D is MQ dash, which is expected horizontal distance between the instrument and the position of the star. V is the vertical coordinate up to the axial hair with respect to the horizontal plane. H is the height of the equipment whereas R is central heretic. Here beta is the angle between the two extreme breadths corresponding to stadia S. So the way we considered earlier, the position of the star is vertical here. In order to deduce the expression, let's make a small construction here. Let's have this A dash C B dash normal to line of sight OC. As such, here angle A dash C being the exterior angle of angle CO dash, its value will be 19 degrees plus beta by 2. In the similar manner, the angle B dash C will be 90 degrees minus beta by 2. However, as beta is very small, angle A dash C and angle B dash C can be approximately considered to be 90 degrees. As such, from triangle ACA dash, from triangle ACA dash, this A dash C can be expressed as AC cos of theta. Similarly, here this A dash B dash can be expressed as S cos of theta. As the line A dash B dash is perpendicular to the line of sight OC, we can make use of expression that we deduced for horizontal line of sight, which is the basic expression D is equal to Ks plus C. Hence, this MC, which is nothing but the distance measured along the line of collimation, which is nothing but L, is K times A dash B dash plus C, which is Ks cos theta plus C. Hence, this horizontal distance D can be considered to be L cos theta. As we substitute the value of this particular L, the expression that we get is nothing but Ks cos square theta plus C cos theta. With similar concept, we can have this particular vertical ordinate of that L as L sin theta. Giving consideration to the value of that particular L, here the expression for V can be determined as Ks sin 2 theta by 2 plus C sin theta. Here, these expressions 1 and 2 are giving us horizontal and vertical distances for the inclined line of sight, which is taken on a staff held vertical at station Q with respect to instrument station P. So as we determine the capital D and capital V, by making use of V, we can determine the reduced level of station Q. With reference to this particular station, as the instrument is set on station P, here we can measure this small h. Otherwise, alternatively, we can have the backside on certain known point of elevation in order to determine the height of instrument. As we determine this particular hi, then we can have it summed up with V the way we worked out earlier, which is nothing but the d tan theta. And in order to work out that particular reduced level of station, we can deduct the R. As such, the RL of the start station is nothing but RL of the instrument station plus H plus V minus R for inclined line of sight, which is in elevation. If the line of sight is in depression, this expression will attain the form elevation of P plus H minus V minus R. So, the discussion that we had till now is pertaining to fixed here method of the tachometry, in which the stab is expected to be held in vertical manner. Similar expressions can be derived if we consider the face of the stab placed perpendicular to the line of sight OC. The expressions can be derived. However, this particular method is very tedious. Defining the face of the stab normal to the line of sight is cumbersome. Because of the wind, because of the displacement of the stab, personal instrumental error, the result would be inaccurate, and hence the method is obsolete. Hence, we are not going to discuss this particular method under the scope of this particular presentation. So another category of the tachometry is tangential tachometry. So we got introduced initially, but just to have a small review. Here, stab hairs of the instrument are not reviewed. Whenever the stab is away, here we make use of stab which is fitted with two targets or brains which are placed at some known distance apart. We measure the vertical angles corresponding to these two targets as θ1 and θ2. The horizontal distance T, vertical intercept V are computed by making use of the distance in between these two targets and the angular measures. This method is said to be less accurate as compared to stadia method. Depending on the nature of vertical angles, that is elevation or the depression, we can have three classes. Say the first class is the case 1, say both angles are of elevation. So the way you see here, instrument is set at station P, stab is kept in the vertical manner with respect to Q. Here the two targets are placed S distance apart, so the distance of that particular lower target is R. Distance up to that particular lower target with respect to the horizontal plane is expressed as V. θ1 is measured with respect to lower target, θ2 is measured with respect to the line sighting the upper target. H is height of the equipment above the instrument station P, and D being the distance in between instrument station and the stab station. Here, the sketch itself is very clear. You can determine V by D tan θ1, as well as here this S plus V will be nothing but D tan θ2. Hence, the S by tan θ2 minus tan of θ1 will be nothing but horizontal distance T. In order to determine the RL of stab station Q, we can go for RL of P plus H plus V minus R. Say, if both the line of sight are in depression, we will be following similar terminology in order to express θ1, θ2, V, R, H, capital T, P as well as Q. The RL of station Q can be determined by making use of expression RL of P plus H minus V minus R, whereas here the capital D can be determined by S divided by tan θ1 minus tan of θ2. As we consider the case 3, here one line could be having in elevation, another could be in depression. As such, here this capital D can be determined by S by tan of θ1 plus tan of θ2, whereas RL of this particular stab station can be determined by making use of RL of P plus H minus V minus R. So the way you see here, the method is totally based on working out the stop intercept and vertical angle measures read by theodolite as theta 1 and theta 2. Calculations are very simple and gives reasonably good results for given circumstances in order to determine the elevation of the stations, which are placed at quite a height wherein ordinary leveling cannot be employed. One more class of the tachometry is using the subtense bar. It is also the indirect method. The way you see here, it involves the subtense bar, which is folded bar having fixed length of 2 meters, which is provided with 2 targets at either end. The way you see here, these 2 targets are kept at constant distance of 2 meters, which can be illuminated by making use of some light source, and the distance in between these 2 targets is kept constant in such a manner that the distance is given by some stable material like invar. As well, in order to have that particular distance fixed, the invar wire is encased with some such non-erodible tubing. Both these particular arms, which can be extended on the other side to give the full length of the 2 meter, are hung centrally. This particular portion is provided with the leveling head, clamping screw, as well small telescope which can assist to set the face of these particular arms perpendicular to line of sight. So the way you see here, we make use of theodolite or tachometer like equipment at the station, and we can set this particular subtense bar at a station up to which we wish to measure the distance. Both the equipment will be centered exactly by making use of normal leveling centering processes. Here, by making use of that particular small telescope, we can refer to the plumb bob hung at the theodolite end. As such, this particular face would be made 90 degrees. So as we do so now, here we can take the reading of this alpha corresponding to 2 extreme rays, say OA and OB, and by making use of this angle alpha and this particular distance of 2 meters, we can deduce the sloping distance as d divided by 2 tan of alpha by 2. As we measure this particular sloping distance, it can be reduced to its horizontal component and vertical component by making use of zenith angle, say Z. Say if we consider this particular vertical direction with respect to that particular vertical axis, we can measure the angle up to this particular horizontal line. As such, here we have that particular Z, and hence we can determine horizontal distance as well as the vertical distance. As we considered earlier, having known the vertical distance, we can work out the reduced level of the station also. The equipment is very sturdy. It serves the quick and convenient method for measuring, especially baseline in triangulation. Here, the accuracy achieved is quite high, say 1 in 5,000 up to 150 meter sight lengths. Here, today one may not be using this particular subtense bar in order to measure these particular distances, but technique as such is very helpful, and the theory should be known to all who are related with land surveying operations. Just last comment, as we discuss about this particular tachometry as a technique. Technique as such is very helpful. It is the optical distance measurement method. But the way you see, here the multiplying constant is 100. So say, if that particular stop intercept is erroneous by simply 1 centimeter, it will be reflected 100 times, and hence the distance measurement will be that erroneous. So, while taking the angular measures as well as the stop intercept, one must take utmost precaution. But technique as such is very helpful whenever any direct distance measurement is not possible. So, I hope the concepts that I try to discuss with tachometry are clear to you. Thank you for your attention. As we move ahead, we'll discuss about the trigonometrical leveling concept. So by till then, I wish you very happy learning. Thank you.